Welcome to the Explainer. Today we are going to untangle a puzzle that shows up pretty much everywhere, from planning a huge project to just compiling the software on your phone. And it all boils down to one simple, really powerful idea: doing things in the right order. So let's make this real. Think about a problem you've almost certainly run into: course prerequisites, right? You can't just waltz into advanced algorithms without taking intro to data structures first. There's a built-in order, a dependency you just can't get around. You know in your gut that some sequences just make sense, like taking CS 101 before CS 201. But what if CS 201 was also a prerequisite for CS 101? Yeah, you'd be stuck in a totally impossible loop, a paradox you could never, ever solve. This little scheduling puzzle is a classic problem. And you know what? Learning how to solve it is a real superpower. So in this explainer, we're going to show you exactly how it's done. Here's our game plan. First, we'll lay out this whole dependency puzzle. Then we'll introduce the official tool to solve it, which is called Topological Sort. After that, we're going to check out two totally different ways to do it, compare them head to head, and finally, see where this incredible algorithm is actually running the world around us. All right, so we've already kind of touched on this, but this idea of dependency is, well, it's everywhere. You have to put on your socks before your shoes, right? You've got to lay a foundation before you start putting up walls. So here's the bottom line. We're dealing with a bunch of tasks, but we can't just tackle them in any old order. There's a list of rules, these prerequisites, that we absolutely have to follow if we ever want to get to the finish line. Okay, so this whole process of untangling this big web of tasks, it actually has an official name. What do you call it when you create that perfect step-by-step to-do list? It's called a topological sort. I know, it's a bit of a mouthful, but the idea behind it is super simple. It's just about creating one valid linear sequence out of a complex network. If task U has to happen before task V, then in our final sorted list, you better believe U will always show up before V. That's it. But there is one huge, non-negotiable golden rule. This whole thing only works if your dependency map doesn't have any of those impossible loops we talked about. In the world of graph theory, this is called a directed acyclic graph, or a DAG for short. Basically, a one-way street system with no roundabouts, no cycles. So, how do we actually find this magical order? Well, let's look at our first technique. We're going to call this one the Explorer, and for good reason. It uses a really common algorithm called depth-first search, or DFS. The Explorer's motto is simple: go as deep as you can, then backtrack. Seriously, think of this method like a maze runner. It picks one path and just goes for it, following it all the way to the very end, to a dead end, before it ever comes back to tell you what it found. So here's how it plays out. You just pick any course to start with, then you dig down and explore one of its prerequisites, and then one of its prerequisites, and so on. You keep going deeper and deeper down this one rabbit hole until you finally hit a course that has no prerequisites left. And only then, once you've hit that dead end, do you add that course to your special list. Now, this is where a cool data structure called a stack comes into play. A stack is just like a stack of plates. The last one you put on top is the first one you take off. So that very last, most basic task you found at the end of your deep dive, it gets put on the stack first. And when you're all done exploring everything, you just pop the items off the stack one by one and boom. It perfectly reverses the order for you, giving you a perfect, ready-to-use to-do list. It's pretty brilliant. But what if we took a completely different approach? Instead of diving deep down one path, what if we just looked at the whole picture at once? Let's meet method number 2, the manager. This one uses something called Kahn's algorithm. The manager's philosophy is all about this: start with what's ready first. See, unlike our deep diving explorer, the manager looks at all the tasks at the same time and just asks one simple question: what can I do right now without waiting for anything else? So here's how the manager kicks things off. The very first step is to go through every single task and count how many direct prerequisites it has. In graph terms, this count is called its indegree. Any task that has an indegree of 0, well, that one's good to go. The process from here is just so systematic, it's beautiful. First, you find every single course with 0 prerequisites and you toss them in a ready queue. A queue is just like a line at a coffee shop: first come, first served. So you take the first course from the queue, add it to your final list, and you say, okay, this one's done. Then you go to all the courses that depended on that one and you knock their prerequisite count down by 1. And if any of those hit 0, You guessed it, they go into the ready queue. You just keep doing that until the queue is totally empty. And you know, one of the best things about the manager's method is this. When you think you're done, you do a quick check. Did you manage to process every single task you started with? If the number of tasks in your final list is less than the total, you have just proven, without a shadow of a doubt, that there's an impossible cycle hiding in there somewhere. No extra work needed. How cool is that? So we've got two amazing methods here, the Deep Diving Explorer and the Systematic Manager. They both get you to the same answer, but they have different personalities, different strengths. So which one should you actually use? Let's break it down, head to head. The Explorer, which uses DFS, is often way simpler to code, especially if you like recursion. It's really elegant. The Manager, Kahn's algorithm, is a bit more work up front, what with the queue and all that counting. But, and this is a big but, look at that middle row. Kahn's has cycle detection built right in. If you're building a really robust system, like a package manager, where a user might accidentally create a cycle, that safety check is an absolute must-have. Now, whichever method you pick, you gotta be careful. Here are a few common tripwires people hit. Trying to sort a graph that doesn't have clear one-way dependencies, that won't work. Forgetting to lower those prerequisite counts in the manager's method, that'll break the whole thing. Or the classic mix-up, using a queue when you need a stack, or a stack when you need a queue. So, why does any of this matter? Why have we spent all this time talking about explorers and managers and sorting tasks? Well, because this thing that sounds kinda abstract is actually the invisible engine behind so much of the technology we use every single day. I mean, just look at this list. Every single time a programmer compiles a big piece of software, there's a topological sort under the hood figuring out which files to build first. It's what powers your project management tool to gray out tasks you can't even start yet. This logic is absolutely everywhere, quietly making our complicated world actually work. And the best part? It is incredibly efficient. The time it takes to run is something called O of V plus E. Now, all that fancy notation means is that its runtime grows in a nice, predictable straight line, with the number of tasks, that's the V, and the number of dependencies, that's the E. So if your problem gets 10 times bigger, the solution only takes about 10 times longer, not 100 or 1,000 times longer. And that's why it scales so beautifully, from a simple college schedule to a system with millions of software packages. So there you have it. We've gone from a simple class schedule all the way to the fundamental logic that powers these massive, complex systems. The ability to look at a tangled mess of dependencies and pull out a clean, clear, step-by-step path forward, that is a genuine superpower. Which really just leaves us with one final thought. Now that you know how to untangle things, what complex system will you build next?